Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.11, a computation that proves associativity. Okay, so another way of thinking about associativity, not just with intersection theory, but but we took all our points on our curve, all the points that there are, and just give them names like A, B, C, D, whatever else. Okay, so we have now if this is a discrete curve, that's kind of nice because we have finitely many of these things to work with, right? These symbols. All right, so we have some symbols, a finite number of symbols, and then let's just take sums of these, like A plus B plus C, or A plus 2B. If you have two B's, you can do that. And let's make it commutative as well. And let's just take all sums of these things with where but we're not restricting ourselves to anything. We're not saying that A plus B is equal to any other point. We're just saying it's just A plus B. So just the kind of the symbolic idea of just freely thinking of sums of symbols where there's nothing attached to it, just like A plus B itself, just even this statement. Let's just take this as an element of a big set. So we're going to form a set, and we're going to say this set is the set of all sums of the symbols which represent the points. And we're going to say that this addition, or these sums are, we're going to say that they're associative. We're going to say that they're commutative, because we're just freely making, this is called a free group on these symbols. And so we're just going to take all sums. So for instance, A plus B is going to be equal to B plus A. And then another symbol is you could have A plus 2B plus C. And this is going to be a completely different statement than like A plus B plus 2C. These two things are going to be completely distinct. It's kind of it's kind of like, if we have like A, B, C, D, E, let's suppose these are our symbols, then it's like we're taking vectors of like um, with integer entries indexed by these guys. Okay, so like 2 or -1 or 5 or 3 and 4. And really, A is just represented by these tuples, okay? Because these tuples can be interpreted as sums of these guys with these coefficients. And if you've taken linear algebra, that's like linear combinations. So basically, what you could think of it as integer linear combinations of 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 all the symbols that represent our points. So actually, we've completely removed ourselves from the elliptic curve, completely no elliptic curve addition structure at all. All we're thinking of is, strictly speaking, this as a group. In fact, if you like, you could think of this as Z cross, if they had 5 different symbols, Z cross Z cross Z cross Z um, cross Z. And we call this a free abelian group. Abelian just means commutative. It's a free commutative group on those elements A, B, C, D, E. Okay, maybe you can abbreviate this as Z to the 5th here, or something like that, where this 5 represents a Cartesian product of sets, where you're just looking at tuples. So that's what A is as a description, is just tuples of things. All right. So do we have a clear, adequate picture of what A is here in the reading? All right. So then what are we going to do with A? We're going to look at a subgroup of A. All right. So let's look at a subgroup, and it's described in the reading here. This is where the elliptic curve structure is going to come from. What we're going to do is we're going to look at points on the curve that actually are in a straight line from each other, that actually lie on a straight line. So if, for instance, if A, B, and C all lie on a line, then we're going to say, and they're in the curve, then we're going to let A plus B plus C be in a subgroup. And we'll just call this H. We'll let H be the collection of all A plus B plus C. So you could think of this as, if this was like Z to the fifth, I mean, this would be represented by a 1, 1, 1. Okay, comma, 0, comma, 0. So basically what we're going to be looking at is we're going to be looking at tuples that have like 3 1s in them, such that those 3 1s represent 3 points on the elliptic curve that actually lie in a straight line. So if we have an elliptic curve, but this is a finite curve, but in general, a discrete curve, but just kind of for picture's sake, if you have like A, B, and C being on the same line, but this will be on a discrete line, meaning the solution of an equation that looks like mx plus b, but in modular arithmetic. Okay, so this is kind of where this b is actually not that b, but get the idea. So, all right, so so that's what H is going to be. All right, H is going to be the collection of all those things where we do that. Now, there's something kind of neat that happens when you think about modding A by H. Now, H is a commutative subgroup, and A is a commutative group, and when you mod out by a subgroup to look at its collection of cosets, operation is always preserved, and you have every subgroup is normal, and so you actually get a group out of this when you look at a quotient. So A over H is actually a group. What about this group? Well, let's think about this for a minute. What if we looked at A plus B for a minute, all right? We know that A plus B plus C is going to be equal to 0 bar when we mod out, because we're making everything in H be like 0. So, so then what does that mean? What if we then had A plus B plus C bar? So we can split this up over, right? We can subtract over the C bar on the other side. So we'll go ahead and subtract over C bar on the other side, and we end up getting negative C bar. Notice what this is. Negative is like taking a vertical partner. C is the third point of the intersection. Oh my goodness. Adding, in fact, and you could think of this as A bar plus B bar if you wanted to, right? So let's do that. Let's think about this as A bar so we get that A bar, and let's see, plus B bar. So this is kind of like, think of this as a point now, like on the elliptic curve describing A, and the point on the elliptic curve describing B is equal to the vertical partner of the point describing the third intersection. In other words, it looks exactly like elliptic curve addition when we just do this quotient, A mod H. So that's kind of cool. But is it like, do we mod out by enough things? We know this looks like this, or do we mod out by too much? What's the size of this quotient? All the cosets are the same size, except at least in an infinite set. I mean, this is an infinite group. A is an infinite group because you could have you could be adding lots of things up, depending on, because you could have different multiples, because we're looking at Z5, right? Z cross C cross Z, so, or something like that. And so, yeah, how do you know if you've modded out by enough? You see this elliptic curve addition rule holding, but how do you know that it matches up, and that you actually have precisely just the elements of the elliptic curve popping out as nice representatives. So to do that, instead of running through all the particulars of that, I wrote a little computation, little program that it actually can compute the size of E, um, the size of A over H of that quotient, and and it turns out to be the same size as the elliptic curve, at least in one instance here, where you can change the elliptic curve as you move along. So this is for a discrete curve in modular arithmetic. You can take a look at this computation and the result, and it works out to actually show you that the size is the same. Now, how does that show associativity? Well, it basically shows that the elliptic curve itself is isomorphic to a quotient of two groups um, that are already groups and already have associativity. And so it's a group, right? It's isomorphic to a group, so it's a group. And so it has associativity. That's just another way of looking at it. Um, and so that was done computationally. Of course, you can do this theoretically as well, but I'm going to withhold, and that's not something that's something beyond the scope of this current text. Thanks for watching.